When using a matrix transformation to transform a shape, the determinant of the matrix representing that transformation provides the scale factor of enlargement applied to the area of that shape. Oh, that was a mouthful to say. Let's just get on with the video. So I want to see if I can get away without ever having to say that title again in this video, but something I am going to say to you is the usual warning, which is... Yes, you don't need to know this stuff for an exam, we're doing it for fun. But another detail you need to be aware of about the fact we're proving today, which is it's better if you include a modular sign around that determinant. And the reason for that is you can of course get negative determinants, but all that minus sign signifies when it appears is just that your matrix transformation involves some sort of reflection as a part of the wider effect it applies, and therefore as reflections have no bearing on the change in size of the area of the shape when a reflection is applied, therefore it's better if we just include this modular sign to make the proof a bit easier to deal with. Cool! But what do we need to be able to do in order to be able to do this proof? Well, you need to be able to deal with matrices and matrix transformations. What a surprise. Not. Considering what we're proving today, that probably didn't come as a surprise to anybody. But what is a bit more controversial is I'm going to require you to be able to work out the area of a triangle based on the coordinates of its 3 vertices. Now, the reason that's more controversial is the more traditional way of proving the stuff we're looking at today is to look at a unit square and to apply the transformation to that unit square and then to see what happens. That's the proof you'll often see in a lot of textbooks, and interestingly, for those of you eagle-eyed, you might have noticed that in the thumbnail for this video I did put a little part 2 in the wording, and that's because I am eventually, one day, planning on making a video that goes to that more traditional proof, even though one doesn't exist as of recording this video. But I thought today, let's spice things up a little bit and do it in a slightly different way, just to add a bit of variety, but also because I wanted to answer a question that a lot of students end up having when they do see that more traditional proof, which is, okay, you can prove it works for a unit square, which shows it works for all squares, but then not all shapes are squares, and not all shapes can be made up out of squares. So therefore, what happens if we want to prove it for any shape? Well, it is worth mentioning there is actually a reason why that unit square method actually is legitimate and why it does prove it works for all shapes, but a more intuitive way of explaining why this determinant scale factor thing works all the time is to instead use triangles, because ultimately any polygon, like for instance a pentagon, can be split up into triangles. So for instance a pentagon could be split up into 3 triangles. So therefore, if you can prove this effect works on any triangle, then therefore it shows by impact of that it works for any polygon, because any polygon can then be split into individual triangles that each individually have this effect applied to them. So that's why we're doing it this way today. I hope you enjoy. Cool, so let's define some things. We're going to start off with a triangle, and of course we need to define its coordinates of its vertices, and we're going to do it in a way so that technically this triangle could be any triangle on coordinate axes, so drawn anywhere and any size, any orientation, whatever, right? So let's say we have one of the corners as something imaginative like x, y, and then you could use any letters you like to also define the coordinates of the other 2 vertices, but I'm going to define them in a bit of a weird way. I'm going to define one of the corners as x plus p, y plus q, and the other vertex as x plus w, y plus v. And that looks a bit weird and a bit mysterious. But the reason I'm doing that is because I'm going to be using vectors as part of working out the area of the triangles for this stuff. And if I define them in this way, it just makes the vectors for the sides of the triangle a bit easier to write out, less letters involved. It seems very specific, but still, you can choose any letter of any value, I should say, of p, q, x, y, w, v, and you will end up being able to draw any triangle on coordinate axes. So this is still a very generalized triangle. We also need to define what matrix transformation we're going to be using. So let's use a very general transformation as well of A, B, C, D. Nice. Let's start off by working out the area of the triangle before we've applied the transformation though, just so we have a baseline before we see the effect of the transformation itself. So to do that, as I already mentioned, I'm going to be using vectors to do this, and I'm going to be using a vector method of half times by the modulus of the cross product of the vectors of 2 of the edges of the triangle. So in order to do that, I need to know the vectors for the edges of the triangle. So this edge would be the vector PQ. Hence why I defined the coordinates of two of those vertices in a bit of a weird way. It's meant the vector for the edge is really nice. And then working out the vector for the other edge by subtracting the coordinates in the correct appropriate way. That will get you the vector WV. Nice. So now I've got those two vectors, we can now apply that method that I said I was going to be using. Now some of you might not know this method, or you might not like it. It's worth mentioning you could do other methods, such as using the two vectors with the dot product to work out the angle between the two edges, and then using that angle with the two edges in half AB sine C. If you don't know vectors really at all, another way of going about this is to use cosine rule to work out the angle between two of the edges, and then to use half AB sine C with traditional lengths to work out the area of the triangle. It doesn't matter what method you do for this, you'll end up with the same answer overall eventually. It'll just take more writing out, more horrible algebra. I did check before doing this video that you do end up with the same algebra. It just does take a lot more writing out, and I didn't want to write that out myself on the video. So there you go. Anyway, the problem with this method I'm using though is it requires 3D vectors in order for it to be able to be applied. And the problem is we've only got 2D vectors because we're dealing with a 2D shape. But there is a way around that. Of course, any 2D space is just a subset of a bigger 3D space. So therefore, you could view these still being within 3D space and just be aware that because the triangle is 2D just on a flat plane, therefore, as a result, you could view the third dimension as being something that's not changing wherever you are on the triangle. So therefore, we're going to rewrite the vectors PQ and WV as the vectors PQ0 and WV0 to signify that third dimension isn't being altered no matter where you are on that triangle. Nice. Now we can therefore apply those vectors in this method. So therefore, half lots of the modulus of the cross product of those two vectors. I'm going to do the determinant method for the cross product, and therefore that's actually going to be quite nice to do because actually a lot of the components for this cross product will end up being 0 because you're going to have q times by 0 minus v times by 0. You're going to have p times by 0 minus 0 times by w. So therefore the only part of that vector will end up being the bottom one that has letters in, which will be p times by v minus q times by w. So you end up with this. Cool. Nice. Now we need to work out the modulus of that vector. The way you work out a modulus, or magnitude, if you will, is by squaring the individual components, adding them up, and then square rooting, which will end up with this. Cool. Now, some of you might be wondering why I'm not just instantly cancelling out the square root and the squared. We'll talk about that more about that later, but just be aware that square root doesn't always cancel out a squared, so that's why I'm not doing that. So, therefore, that's the area of the original triangle, and therefore, moving on, now let's see what effect applying the matrix transformation has to this triangle. So, therefore, we are going to take our transformation and apply it individually to the three vertices coordinates, or position vectors, if we're trying to do it using matrix transformations. So, multiplying these three matrix multiplications, we can do this, we can do this, and we can do this. So that's the three multiplications done. Admittedly, that second and third multiplication could then be simplified because we've got brackets we can then multiply out. So that second vertex could have a position vector that simplifies to this. I say simplifies, that looks horrible, but anyway. That third vertex will also simplify to this, or rewrite, I should say. Maybe that's a better way of saying it. Cool. Now we've got the three vertices of the new transformed triangle, we can now try and work out the area of this transformed triangle, going through pretty much the same process we did as before, working out the vectors for the edges by subtracting the position vectors in an appropriate way. So doing that first subtraction, interestingly, things are going to cancel out, which is quite convenient. The AXs and the BYs are going to cancel out, meaning we're just left with AP plus BQ plus, or not plus for the Y coordinate, CP plus DQ. And then similarly for the second vector for the other edge, if we simplify that, stuff is going to cancel out, and you're just going to be left with AW plus BV, and then CW plus DV. Cool. So we have got vectors for two of the edges of the triangle, Again, applying the exact same method we did before to work out the area of this new triangle. But to do that, of course, first convert them to 3D vectors. Brilliant. So now putting them in the same method as before, we're going to do the cross product. That's a bit more horrible to do this time. So therefore, it's going to be for the I component, again, basically a lot of zeros because we're going to have, the diagonals multiplied by the zeros. Same for the J component, but the K component, got to be more careful. We are going to have to do this times by this, and then we're going to have subtract this times by this. And that will therefore mean we end up with this, which looks really horrible. So the next thing we're going to do is to realize that we are going to multiply the brackets. So we could first multiply those first pair of brackets and get the things you can see on the screen right now. And then if you subtract what you get if you multiply out those second pair of brackets, you'll end up with all of this, which is really horrible to write out. But the good news is some of that stuff is going to cancel out. We've got this cancelling out with this. We've got this cancelling out with this, which means it's only all that other stuff that's going to be left over, meaning we've got this as our simplified vector for the cross product. We've now got to calculate the magnitude of that, and so therefore we might choose to do the square root of the squared component that we've got there. But at this stage, it's kind of difficult to just look at this and instantly be able to spot why this is just the determinant of a matrix transformation applied to that area of the triangle we had before. So we're going to do a bit of factorizing to help us out. So I am going to start by rewriting the same thing but in a different order. So I'm going to just rearrange the order I've written those individual components, or terms I should say, so that it's a bit easier to now factorize, because instantly you can maybe spot that those first two terms then both have an AD factor, and both of those second two terms have a factor of BC. So therefore, we're going to end up with this. I have also chosen to factor out minus BC out of those second two terms rather than just BC, and you'll see why, because now it means we've got a factor of PV minus QW in both of those things, which means we can factorize that out of the entire thing. So therefore, we end up with AD minus BC, lots of PV minus QW. Nice, you can probably see where this is heading now. If you now apply index laws with the squared and the square root both being able to be applied to those two pairs of brackets individually, we will therefore end up with this thing like this. Cool, we're almost there. Just one final thing to be aware of. This is where we need to talk about the effect of square rooting a squared thing has. So let's take a look at numbers. Be aware that if you have a positive number squared than square rooted, if you square, for instance, 3, you'll get 9, and the square root of 9 is positive 3. But interestingly, if you do the same effect to a negative number, let's say we're squaring minus 3 and then square rooting, when you square the minus number, it will come out as a positive number again, but a square root will always still have to come out with a positive number. So therefore, interestingly, the effect of square rooting something that's been squared is the same as doing the modulus of that thing. So therefore, the square root of AD minus BC all squared is the same as the modulus of AD minus BC. And so therefore, I've taken that out now as a factor out the front, moving the half so it's next to the other thing we had. And that's interesting because now it means this thing here is just the modulus of the determinant of our 2D matrix transformation we're looking at. And then this other thing that we're multiplying by is, of course, that result we got when we worked out the area of the original triangle. So therefore, boom, we've proven it. We are done, and that is all I wanted to show you for today's video. So, with all that said, consider checking out some of the other videos I have. I've got an entire series of Prove It videos on this channel where we prove everything in the A-level syllabuses, so take a look at those. And also got my Can We Do That series where I extend things and explore areas of maths further and beyond. Please like and subscribe to my channel.